very good morning to all of you. On behalf of the Department of Physics, we take great pleasure in welcoming the gathering to the most awaited event of this academic season, the ninth Professor K.M.Karunakaran Endowment Lecture. The year was 1921. The man who changed the landscape of physics forever gets the prize. Yes, Albert Einstein got the Nobel Prize in Physics in 1921, a full century ago. Although the prize was awarded ostensibly for the photoelectric effect, we all know that the prize packed in all the weight the legend deserves. The world celebrated the year 2005 as the year of physics, for it was the centenary of Einstein's four seminal papers. In the same spirit, we can celebrate 2021 as a centenary for the award of the prize itself. And that is our agenda for today. And we are doing it in style. We have a legend with us, a stalwart amongst physics teachers in this country, a teacher who has changed the very landscape of physics teaching and learning in India, Padma Shri Professor H.C.Verma. On this occasion, Professor Verma will share his insights about this very contribution of Einstein's that we are commemorating today, the photoelectric effect. But before we get started, I request all of you to join with us in the opening prayer. I ask Mr. Nitin Joshua, the General Secretary of the Physics Society, to do the invocation. Nitin, please.
Thank you, sir. Important prayer. Heavenly Father, thank you for giving us this beautiful new day. I thank you for blessing us with this ninth Professor KMK Endowment Lecture. Bless the speaker of the day. Bless the people who helped us to prepare for this day. Bless all the listeners who have come from various places. Bless all the dignitaries who have joined with us today. Help us to make this day a memorable one. I commit everything in your mighty hands. In Jesus' name I pray. Amen.
We'll follow this with a prayer song. Just wait for a second.
Sweet art of prayer, sweet art of prayer that calls me from a world of care and bids me at my Father's throne make all my wants and wishes known in seasons of distress and grief. My soul has often found relief and doth escape the danger shared by God without the hour of
These are challenging times. I'm not talking about the pandemic, but the perception of the younger generation on the fundamental science. We have with us the modern technologies, machine learning, AI, big data, and they seem to rob the charm and obviate the importance of fundamental sciences. Do they? It may seem so. But on the contrary, physical sciences with mathematics are hard sciences that will never go out of fashion. And they fuel future technologies. It is not my prophecy, but this is what Naval Ravikant, a tech guru and a co-founder in Silicon Valley, says. This event today is a celebration of the past, no doubt about it. But it is an effort to rekindle the very spirit of inquiry into the wonders of the nature. It is a reaffirmation to realign the young minds to turn to physics and fundamental sciences. Now, in this effort, we are celebrating this event, and I call upon our head of the Department of Physics, Professor Samuel Asirvadam, to formally welcome the gathering. Asirvadam, sir, please.
A very good morning to all. I thank the Lord Almighty for His grace upon us to be able to hold this prestigious endowment lecture on this day, in spite of all the difficulties we are facing. I deem it a privilege to welcome the speaker for the day, Professor H.C.Verma, sir, a renowned physicist in India and an ardent researcher, and above all, a fine, exemplary human being. I sincerely thank him for taking his time to be with us to deliver this lecture. I also thank our principal for being able to be here to offer the felicitations. I warmly welcome all the faculty, former faculty members, the physics alumni, and all of you for this prestigious endowment lecture. Also, I welcome a special welcome to the Physics Alumni Society office bearers, very specially to Dr. N. Lakshminarayan, the president of the society, then Dr. Sam Paul, the secretary of the Physics Alumni Society, and all the executive committee members. A warm welcome to our beloved faculty members of the department and all the students, all our dear students. Very importantly, I also welcome all the students and faculty members of the colleges in the city, for whom actually we have given an invitation very recently. So they were able to join us. So on that count, I thank them. I thank, actually, I'm an ardent reader of the Concepts of Physics book by Professor H.C.Verma. So I feel elated to be able to listen to him in one of our programs. Before closing, I wish to place on record with thankfulness the tireless efforts made by Dr. Caroline Victoria as convener of this endowment lecture. So once again, a warm welcome to each and every one of us, and I'm sure that everyone will be benefited by this great endowment lecture. Thank you.
Thank you, sir, for your kind words. Welcome. Next, I will call upon Professor N. Lakshminarayan, the president of the Physics Alumni Society, to address the gathering by delivering his presidential talk.
May I?
Yes, sir, please.
Yes. Very good morning to all. The warmest greetings and welcome to Professor Verma from the Physics Alumni Society. Our respectful greetings to the principal, and thanks to him for gracing this important occasion. The Physics Alumni thank the head of the department, Dr. Samuel Asirvadam, the staff advisor, Dr. Caroline Victoria, the support staff, and the wonderful students of the physics department. What I briefly will say now is for the interest and information of Professor Verma himself and some of the younger students who might not be knowing a lot of facts. The Physics Alumni Society formed itself in 2010, mainly for the alumni who have obviously succeeded very well in society, in the world, to give back to the department. With the aid of the executive committee, again consisting of leaders amongst our alumni and the staff of the department, we have been talking about various programs. A lot of things have been done for the department. Most importantly, the currently ongoing scheme is the financial assistance to deserving students of the department, which is going along beautifully, wonderfully, and makes all the alumni who contribute feel so happy about it. The main strength for the conduct, coordination, and carrying on of that scheme has been our pillar, Dr. Sam Paul Damodaran, the secretary of the department of the Physics Alumni Society. When we formed the association in 2010, as an important event which will add value to the department, the alumni thought of starting this endowment lecture, and we started creating a corpus for that. And as far as I know, the HOD tells me that the current amount is around 5 lakhs or more and still accruing. This endowment lecture was, of course, on a consensus amongst many of the alumni at that time, called as the Professor K.M.Karunakaran Endowment Lecture, because he was a teacher of great repute, a beautiful teacher, a wonderful teacher. In a sort of way, this event, an important event in the calendar of the physics department, and a very important signature contribution of the physics alumni, is a celebration of KMK, as well as the celebration of the physics department itself. I don't know how many of the younger students of the department and maybe staff themselves of the department realize, Professor Verma must be knowing it, that our illustrious alumni were at the formation of Indian science itself from the beginning, starting from K.S. Krishnan, Rajaramanna, Rajsekaran, E.C.G. Sudarshan, so many big names, Professor Matthews here, Professor G. Venkatraman, all NCCNs. And it's such a great reputation which we have to stand up to and which gives us great value whenever we go, wherever we go in India. Now, let me just briefly talk about Professor KMK. Professor KMK was my teacher, our teacher. We used to look forward to his class every week. It was a great experience. The style of that man, such a handsome man, and the way his language just flowed out of him, and the clarity he gave to the subject he taught. Quantum mechanics was a subject he taught us in PG classes, and so many of you people don't know that those days we saw quantum mechanics only when we came to PG, and Professor Verma sure knows that. It is always said that nobody really understands quantum mechanics. I call it a bundle of lies, true lies, because it is the subject which has given you all the technology which we now enjoy in the world. And Professor Karunakaran demystified that subject beautifully, so that we thought that confusion was the simplest confusion for us in the entire PG courses. Professor Karunakaran was such a teacher. And to quote Professor Arthur, one of his closest colleagues, friends, trusted friend, and I would just like to quote that, sorry, just a moment, yes. Professor Karunakaran was a wonderful teacher, and let me also add that he was the best amongst peers. I think even now or at all times, MCC's physics teachers were highly committed and very good. And obviously, Professor Karunakaran was the best amongst them and the star amongst them. He was slightly better than the others. In the words of Professor Arthur, his friend and colleague and equally good teacher, Professor Karunakaran as a teacher was a man apart. he would, like a Buddha, smilingly watch our antics because he could handle any subject with a mastery that was unique. To him, every lecture was a performance. Ladies and gentlemen, we enjoyed that performance for 1 year when I studied in MCC, and as a colleague of his later for some time. Professor Karunakaran was a great teacher, and it is very befitting that we have Professor Verma to deliver this endowment lecture. I heard a lot about Professor Verma. I have not listened to him, but on the recommendation of the students whom I have assisted, I have a set of his concepts in physics with me. And I suppose it needs his teaching abilities and skills and elan needs no more authentication than his books. Thank you all.
Thank you, Lakshmi Narayan sir, for your golden reminiscences of the character of who K.M.Karunakaran sir was. And the younger generation got a glimpse of the personality. And now, without much ado, I would like to request our beloved principal, Dr. P. Wilson, to felicitate and address the gathering. Sir.
Good morning, everyone. Indeed, it's a delight to be with the Department of Physics this morning in felicitating this particular lecture in name of Dr. Karunakaran. As Dr. Lakshmi Narayanan mentioned about Professor, we all should remember and go back retrospectively and think about how this quantum mechanics started developing after 1900s, when Planck was able to propose E is equal to h nu, and when black body radiation was not able to be explained using a classical electromagnetism, classical mechanics could not explain it. And people were thinking that it was intensity that is proportional to energy. And all around there was a struggle in explaining how this black body radiation could be explained. Wien's law, Stephen's law, nothing could explain the concept properly. And at that time comes this explanation from Einstein. Probably we should say that it was not Einstein who discovered the phenomenon, but he explained the phenomenon and published it in 1905. And looking at the history of science, reading history of science is so interesting to see that Einstein was the one who completely made a paradigm shift that it is energy that is proportional to frequency, and asserted it after Planck's law. Just made use of Planck's law and asserted it, and finally explained the photoelectric effect. We all know this. And as we discuss now, Dr. K.S. Krishnan, who moved from American College to MCC for pursuing his BSc Physics, completed his BSc Physics, and he was looking for a job, and it was only Department of Chemistry could embrace him as a demonstrator. I read it in a He joined as a demonstrator in the Department of Chemistry because there was only one vacancy in chemistry. It was in the older campus, not on this campus. And Dr. K.S. Krishnan was well known for his lunch hour classes all around Chennai, where students from all around Chennai, including other colleges, used to come to K.S. Krishnan to listen to him, even from presidency. They used to come and listen to him during lunch, and he used to handle even classes from chemistry, physics, sometimes in English too. And then he moved on to University of Calcutta to join Professor C.V. Raman for his PhD. So I was just going through some of the archives material about K.S. Krishnan's, his attendance and all those things, because I was interested a bit on history of science. Such was a trend-setting college, that Madras Christian colleges, as Professor Lakshmi Narayanan mentioned, that it was during that time, 1900, maybe we can say that some of the papers were appearing probably 1920s, some of the reviews were appearing probably 1930s or 1940s. Maybe few books could have come by 1960s when Dr. Karunakaran was handling this particular topic on quantum mechanics. Just remember about it. I remember LRG, we call him as in Madras College. He used to handle quantum mechanics. It was that time that he had to read mathematics on his own. He has to read some physics books on his own. He had to read some chemistry books. There were no chemistry books on quantum chemistry as such. So he was teaching. So this is kind of a time where you have to collect materials, compile materials for the forthcoming years. This is how the context is. So I really would like to see the glorious past of Madras Christian College, where Dr. Karunakaran was handling this quantum mechanics, and he wrote a book and was even known among the professors from the University of Madras. So I'm very happy that sometimes when reading the history, science motivates us, triggers us to do research much more. So it was Einstein who worked during the time of patent office. When he was working, he proposed this theory of relativity. And we all know Einstein did not think God would choose to play dice with the universe, because quantum mechanics based on probabilities and choice. And sometimes when there is a trend-setting things happen, we need to humble ourselves and accept the fact. I'm sure that the Department of Physics laurels in coming years, where we would also produce such students from the Department of Physics, where we'll be breaking the classical understanding of concepts, and we'll be traveling into the new era of physics. Thank you very much for inviting me. I wish the department all the best.
Thank you so much for your felicitations, sir, and your kind words of encouragement. Members of the Physics Society of the Department of Physics have worked very hard to conduct this event, especially the staff advisor, Dr. Carolyn Victoria, has played the pivotal role in conduct of this event. Now, I request Dr. Carolyn Victoria to introduce the speaker to the gathering. Victoria, ma'am.
Can you see the screen, Norman?
Yes, yes, ma'am, you can go ahead. Yes. The screen is fine.
1 second. Is my video on? I couldn't see that.
Yeah, your video is on. Your slides are also on.
Good morning, ladies and gentlemen. It is my honor and pleasure to introduce one of the living icons of physics education, Padma Shri, Professor H.C.Verma, to the audience. When we were choosing the dates, Verma sir opted for 8th April. Then I didn't realize what is the reason. But now after seeing through his website, I found in 1952, he was born this day. Happy birthday, sir.
Happy birthday, sir.
Thank you. Thank you very much.
Happy birthday.
I think the students wants to sing for you, sir. Happy birthday. Are they? Fida?
Yes, ma'am. Yes, ma'am. Can we, ma'am?
Yes, start. Yes.
Happy birthday
to you.
Happy
birthday to you. Happy birthday to you.
Happy birthday, dear sir.
Okay.
Happy
Thank you.
birthday,
Thank you,
sir.
students.
Okay, thank you very much. Grateful.
And, to talk about Professor Verma, I don't have any worthy. I'm not worthy enough to talk about him. But anyway, to introduce to you, I like to say some of the details I've got in his website. He did his PhD in the title Studies of the Electric Field Gradients, and he has been supervised by Professor G.N. Rao and has guided 11 PhD theses and have published 134 research papers in reputed journals, and citation of very high value and H-index of 23. And in 1979 to 94, he worked as lecturer and reader in the Science College, Patna University, and then retired from the Department of Physics at Indian Institute of Technology, Kanpur, as a professor. His research interest has been in nanofabrication using focused ion beam, magnetism in graphite on irradiation by ion beam, and nano-size magnetic materials, Fe-based alloys, earth sciences, etc. And this is the important thing which grabbed our attention, and major contribution towards the physics education was from these books. And most of us students as well as the faculty would have been benefited or inspired to physics by these books. From class 9 to class 12, CBSE has recognized his work and recommended these books for the students. And of course, a book on quantum physics, and there are still 2 more books on the road to get published. And teaching is his forte, and he has developed more than 600 physics experiments done by student teachers, and these can be used as a demos in these classrooms. And almost every year he was adjudged outstanding instructor or tutor as announced in the Senate of IIT Kanpur, and has been recognized for his physics education throughout the world. He has also produced a set of 45 video lectures, which is very popular among us. Many of us have watched his video lectures for the school level, but very much helpful in understanding the basic physics. And Utashi physics teachers and demo experiments is one of his interests. And major thing is, I have to mention this, is Professor Verma's contribution to the social cause. And Professor Verma has been associated with social cause from his childhood and instrumental in making a group of IIT Kanpur faculty members and students together with local youths to run an NGO called Shiksha Soban. And now after his retirement, he is totally devoted to this social cause. And through the Shiksha Soban, they have lots of activity, varied from activities to scholarships and education, in particular to rural people. And he has brought the IIT faculty to the rural areas of Kanpur, and he is in touch with around 250 families. And so he just teaches with the help of a voluntary group. He teaches and it takes education to the rural public. And it's one of the another concept is IAPT, that is, he is an executive committee member of Indian Association of Physics Teachers and tirelessly works for the physics education in schools and colleges. And he has many national projects. One important project is National Avanshika Network. And it became the flagship program of IAPT. And many chain of science laboratories has been done by these innovative works of students and teachers. And very importantly, another dimension of Sir is on the talks on sciences in ancient India. Professor Verma has deep interest in the glorious tradition of science in ancient India. And he has done lots of literature, researched lots of literatures and journals on this topic. And in his talks on mathematics before zero, computational sciences in ancient India, surgery, a 9,000-year-old tradition in India, have been widely appreciated by the audience. And due to these works and other works, he has been recognized from the government of India, Maulana Abul Kalam Azad Shiksha Puraskar by the Bihar state government. And wonderful is he was awarded the Padma Shri, India's 4th highest civilian award in 2020. Congratulations, sir. And we are very proud of you and very happy. And I wish to say one thing, like you are the most popular speakers we got. And our students, you're on popular demand from the students. That's why we wanted you to address our students and our teachers and other well-wishers of physics. Thanks a lot for accepting our invitation, and thanks a lot. We are very eager to hear your words. Thank you, sir.
Thank you.
Thank you, ma'am. And now the wait is over. The long wait is over. I request Professor Verma, sir, to take the mantle. Verma, sir.
it is very difficult to start because it's so emotional and so touching. This half an hour, knowing about the college, knowing about your faculty, knowing about the Alumni Association, then Dr. Karunakaran. It's so touching and so emotional. So I'm really feeling very, very happy to be here in this event. Thank you, Principal Sir. Thank you, HOD Sir. Thank you, Nirmalji. And of course, Carolyn Victoria, Madam. And knowing about Professor Karunakaran really resonates with my vibrations, because from the very beginning, when I was a school student, my dream was to become a teacher. And although I did researches and I did PhDs and published papers, and I enjoyed all those researches, but somewhere every time in the background I had that once I get the opportunity to become a teacher in some school or college, I will be the happiest person. And that I got just after my PhD was over and I joined Patna Science College. So that was about teaching, and anyone whom I see is a teacher by his heart or her heart, and exerts for it, for good teaching, for meaningful teaching. I find that, okay, I'm there. I am there. So it was so nice that this lecture series has been instituted in the memory of that great person and great teacher. Quantum mechanics was his favorite subject, which he taught in those days, early days. And I also have some stories with quantum mechanics. I started my quantum mechanics again when I was in MSc. That was in the year 1975. And the teacher who introduced quantum mechanics to me is also a wonderful teacher, retired long ago, Professor A.P. Shukla at IIT-K. And it was his teaching, it was his course that felt me that this is a really wonderful topic, and a blend of imagination, a blend of abstractness, where the direct experiments are not there to see, but then the consequences of all those imaginary quantities. When I was studying in my BSc or my intermediate, we always thought that what are the use of these complex quantities, square root of -1? But then once the quantum mechanics was there, then we thought, okay, good, mathematicians have done a good job. They had given us this ready-made quantity root over -1, which played such an important role in quantum mechanics. But at the same time, when I was in IIT Kanpur for doing my MSc, I did 20 courses there during my MSc, and then 4 courses, pre-PhD courses, when I was enrolled for PhD. In all those 24 courses that I did at IIT Kanpur, in 23 I got A grade and 1 I got B grade. And the course in which I got B grade was none other than quantum mechanics. Okay, the subject which I liked most, the subject where I really enjoyed the course and the subject, everything, that was the subject which deprived me to be 10-pointer during my MSc, but that never diminished my love and affection to quantum mechanics. And finally, this book, Quantum Physics, which I wrote recently, say 10 years ago or so, is also being welcomed by the students. So I feel very, very proud of this particular subject. Now, regarding the birthday gift that I got was a really surprise, because my birthday is not 8th April. If I go by dates, it is 3rd April. I think 3 and 8 look quite similar to each other. Therefore, the website, whoever is written, have made this mistake of putting. But then if you get something for which you never have any clue, it's always a a real gift, God given gift. And but I really remember my birthday as Ram Navami, because in 1952 I was born on the day of Ram Navami, and the whole India celebrates Ram Navami, and I think that yes, that is a celebration of my birthday too. But thank you very much for this happy birthday wish and all those things. Now, coming back to this topic of today, the history of photoelectric effect. The history of exploring this history is also very interesting, because photoelectric effect, maybe as is there, it's a wonderful phenomena. And when I studied it in my class 12, I really was very impressed by the kind of photon picture is there, and then the wave picture is also there, and both coexist, and both are there on the same table. On one side with the same light source, you can put up an experiment where you see the diffraction pattern or interference pattern, and from the same source on the other side you can set up a photo cell and then see that discrete nature and then the photon picture. One experiment is not explained by the waves and other is not explained by the particles. So these things really fascinated when I was in schools and colleges. And then when I became a teacher, I started teaching with the textbooks, the standard textbooks. Then there were mentions of some experiments, okay, some experiments where people observed that the stopping potential depends on the frequency and blah, 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 not on the intensity and this and that. But I had never seen the original literature or description of the experiment as such. What we saw in the class, in the textbooks, was the results, some plots, and not the original data plots, but some sketches by the authors, probably simulated from that Einstein equation, h nu equal to that, what, half mv square plus pi and so on. So probably from simulation only they plotted that graph and then explained all the things there. And I was always trying to see who did these experiments and where are those data. And initially there was no internet facilities, no Google searching, and very difficult. Patna Science College, we did not have journals. And therefore I just used to teach what is there in the textbooks. But later on with this advance of technology, when we have now everything on the net, then I started searching that who did what. And I found that, okay, the story is very, very interesting. And it's our students are not at all told about those things. And therefore, now I'm writing Hindi version, not Hindi version, but a book comparable to this concepts of physics in Hindi. And there I'm introducing this history of photoelectric effect, the historic experiments related to photoelectric effect. And that is how this idea of giving talk on this particular subject, 2021, as you said, that 1921 Einstein got Nobel Prize for this photoelectric effect. So this year is a kind of centenary celebration also. So that is how this whole thing came into. So now I'll start with, because it's already 3 minutes past 10. So I will go straight to my PPT, and then I'll talk on this photoelectric effects. It's hurriedly made presentation. Okay, there's so many things are there that it's only a few hours before the time I could sit on this, and very hurriedly I prepared this presentation. So excuse me if you find that it's messy and not very clean, but let's see what it is. So I'm sharing the screen. I think it should be there. All right?
Yes, sir. Clear, sir.
Oh, very good. Okay, so the story of photoelectric effect, we can start with, okay, let me see, here. Now, this is one phenomena which which is associated with 3 Nobel Prizes. In 1905 is Leonard, 1921 is Einstein, and 1923 is Robert Millikan. Okay, so some way or other, this photoelectric effect is associated with 3 Nobel Prizes. That's also very interesting data I found. All right, so to just give a small brief background, everyone knows that Sir J.J. Thompson discovered electrons, and Crookes tubes were there, which were studied for current through gases at low pressures, and those cathode rays were discovered. And Thompson did a lot of experiments in 1897 or so in that period. And this particular experiment of 1897 is celebrated as the discovery of electron experiment. And he could measure E by M. This is also a textbook stuff, that we have this vacuum tube, and then the cathode there, anode there, potential differences there, and then you have these gases. Okay, these gases, and these gases are supposed to get dissociated in electrons and ions, and those electrons which are known as cathode rays. So they were studied by applying electric fields and magnetic fields and the deviations, and then to neutralize the deviation by electric field, by magnetic field, and to make the path straight, you need a particular value of E and B, and from there the velocity, the speed of the electron is related, and with that speed, this this potential which is applied between cathode and anode, that is related, and that is how E by M is obtained. Now, reading these original texts widens our thinking also. Now we do these experiments in our classroom, maybe in BSc, maybe in MSc, in laboratories, a routine experiment, could be a routine experiment. But when you read the original writing of these physicists who have done these experiments, then you learn to know that it was not there. They thought of the principle, they thought of a design, then they made a design, they fabricated the tube, they put all those materials inside and performed the experiment. So that that attribute, that parameter, that if nothing is there but I have an idea, then I can design my apparatus, I can fabricate my apparatus, I can assemble my apparatus, and then I can perform the experiment, and not that you do it and you get the result. Very obviously, so many trials must have been made to get this final presentable version, where this reading these original texts, original research papers is very not only informative, it inspires that yes, this is how one should go about it, this is how history is made. All right, so, and any gas you put in this discharge tube, any material you put for the cathode, any material you put for the anode, all the time this E by M comes the same, and that establishes that okay, there's some fundamental negative charged particle in all the materials, and that is how the electron is established. But this was E by M, and then Robert Millikan comes in, which designs yet another wonderful, beautiful experiment. Beautiful. I performed this experiment during my MSc, this Millikan's file drop experiment. But to think of a design and then to make these apparatus and then perform the experiment and then come out, standardize that and make it much more and more sensitive, and then you come out with a very fundamental result is something really inspirational. So there must be this physical society may promote this kind of reading much more, and presentation by students on these type of original research papers could be really useful. Okay, so E was there, E by M is there, electron is well established, cathode rays properties were well studied, and all those things. Now, the history, perhaps the recorded history, okay, or at least the one which I could reach. So that probably starts with this Hertz, and the Hertz was the lifespan was very short. He died in some 36 years of age or so. But during that only he made really historic experiments. And this is the Maxwell's equations were there, and from the Maxwell's equation, it was established that one should have electromagnetic wave. The equation, the mathematics gives, right? The equations are there because of some experiments, but not the wave experiments. All these divergence and curl of E, etc. They come out with from the experiments on charges and currents and magnetic fields and electric fields, but not the waves. But once the equations are there, the equations when you manipulate predict that there can be a wave, electromagnetic wave going with certain velocity. So that is the connection between experiments and theory. All theories of physics, or all theories of science start from some experiment, some phenomena that we see. But to understand that phenomena, to understand the data, to understand that experiment, we formulate theory, basic theories, and we try to understand the inside of the nature which governs all those experimental results, all those phenomena, all those events. And when we formulate our theory, the theory tells other things which were not seen yet in the experiments. And then the experimentalists will start working on that, will perform experiments to verify that, okay, if the equations are telling this, it should be there. So design the experiments once again, design the operators, and then do the experiments, come out with the results. And when they come with the results, new experiments, new results, so okay, those theories are verified or not verified, but you have new data. And once you have new data, again, the need of a new theory might come in. So that is how this experiment and theory go side by side, and physics is a real good interplay between the two. All right, so this prediction was there, and Hertz set out to produce these electromagnetic waves in the laboratory, and this is how he did it. And one side he made a circuit where high voltages were applied, and all those oscillating circuits were there, and sparks were produced between these balls. And on the other side of the lab, a few meters away, he put this sensor on the right of my screen. I have that sensor. This once again a small gap between two copper small balls, and the electromagnetic wave which travels from this left side circuit where the sparks are produced by the circuit, they reach there without any wire or anything, and then create a spark there on that this right side sensor. Okay, so this established that yes, the electromagnetic waves are there. So Hertz could produce these electromagnetic waves in the lab. But then, as I said, when you do an experiment, you design an experiment to check whether the prediction of the theory is going well or not. Then you also produce something. The experiment is experiment. And the experiment can also give you some more information. Nature can reveal some more data to you, which you did not demand for. Okay, and that was a side effect which was mentioned by the Hertz. He noticed, and not only noticed, he he worked on it, but not very seriously, because the main agenda was to show that yes, there's something called electromagnetic wave which can travel in vacuum or in free space without any material, without interacting with the material, and then can go from one place to that place. And that was fulfilled, and that was the main part of that Hertz paper. But then he mentioned that something else. And what was that something else? And that something else was that the sparks on this right side sensor were feeble, because of course the electromagnetic wave is diverging in all direction, and the intensity which reaches this at a distance will be small. To see the spark, the light condition should be dim so that you can see the spark. So some kind of a shield was put in front of that sensor coil so that light can be restricted and the spark could be seen better. And then he finds that, okay, when we shield it, sometimes, depending on what material we are putting there, sometimes the sparks become even longer, even better, even sharper, and sometimes they become shorter. So it depends on what kind of shield we are putting. And then Hertz did some experiments with different kinds of shields, and then he came out with this side result. Apart from establishing or producing the electromagnetic wave in the lab, this side result that if I put a shield which blocks UV light, then these sparks on the B side is diminished. And if UV light is not blocked, visible light is blocked, okay, then the sparks are longer. So he mentions these results, that this UV light is doing something and then leaves it there. Now there is an assistant to this Heinrich Hertz, and this, okay, so this is the thing which he mentions, but then he doesn't explore further. And then this person, this Hallwards, who was an assistant to Hertz in that EM wave experiment, he takes up this, a separate experiment he designs. And his experiments, as the literature says, were of some demonstration type, a very simple experiment to investigate this phenomena of action of ultraviolet light on this metallic balls which were there in the sensor. And that was this kind of arrangement, which after reading this Hallwards report, I performed this experiment in my laboratory. It's a very simple experiment to perform, and anyone can do it anywhere, in any college. What you need is a very simple system where you have some kind of a metallic plate, zinc plate, Hallwards had taken, but I had taken aluminum plate in my laboratory. Put it in on some insulated stand, then take an electroscope, and firstly, separately charge this electroscope with some negative electricity. So I never remember which material rubbing on which material gives me which side becomes positively charged and which side becomes negatively charged. So that I never remember. The school textbooks always mention that if you rub this glass rod on an woolen cloth, then the glass rod will acquire something, either positive or negative electricity. So I also did various combinations. So I took different materials, rubbed it with different materials, different kinds of cloths and things, and then did the experiment. So as Hallwards has written, the similar results were obtained in my experiment also. So electroscope you take and then you charge it with negative electricity. I don't remember, I had done this experiment a few months ago. Some perhaps plastic straws, this drinking straws, I rubbed with some kind of cloth, and that worked very well. So if you give negative electricity to this, and how to charge an electroscope? Very simple. You bring this charged rubbed rod close to this top of electroscope, gold. Its name is gold leaf electroscope. By the way, I had not purchased it. I have just prepared it in my laboratory. Just took a plastic bottle, transparent plastic bottle, and put a vertical copper rod into it. And then in a loop, I put 2 aluminum foils, the kitchen foil that we use to wrap our food. So 2 small pieces of that I put on this copper rod inside this plastic ball, and my electroscope was ready. But its name is gold leaf electroscope. Okay, so you need not really go for gold. You can work with aluminum foils also and make your own electroscope. All right, so you bring this charged rod near the top, don't touch it, and then touch with your finger this rod, so that then you remove your finger in presence of that rod, and finally remove the rod. That is the way I had studied in my class 8 textbook, how to charge a gold leaf electroscope. So do it. So keep it negatively charged to start with. All right. And then on this side where you have this I used aluminum plate, Hallworth used zinc plate. On this side, you have to shine UV light. So either UV lamps are available in market, you can use UV lamps, or magnesium chemistry school textbooks say that properties of magnesium. So magnesium ribbon, you can burn, and then it gives a lot of light and also some smoke, so pollution will be there. So better not to use that, but I use this magnesium only because that time I didn't have UV lamp. Now I have purchased it. So UV light falls on this zinc plate, and then you see that these leaves in the electroscope, they behave in a certain way when this zinc plate is connected to this electroscope now. So what is the phenomena? The phenomena is UV light will eject the electrons and will make it positive. All right. So if it is already negatively charged, then these foils will come closer to each other because the charge will go away. And so on. So you do this experiment and see. So Hallworth experiment is only this. At many websites, I have seen that in the name of Hallworth, they have mentioned that this was measured and that was measured, but I could not find the paper where all these things, all these measurements are mentioned. But nevertheless, this is a very good experiment, very nice experiment, which can be done by us also very easily without much of arrangement. So that is was there. But the real important experiment came from this Leonard, and sometimes in 1899 he took up this task specifically, designed his experiments, his apparatus. This is the kind of experiment, this design. This I have taken from that Nobel lecture that Leonard has delivered. From that, this is there in that write-up. And you can see on the left side, you have this this cathode, and vacuum tube is there. And this vacuum tube on the lower side, you can see that inclined line where WW is written. So there's a window, a transparent window through which the light is sent inside this vacuum tube. From outside, light is sent inside, and that falls on this cathode. And then the cathode rays, that time it was called cathode rays, not electrons, but now in our language, electrons are ejected. And then those electrons are studied. The behavior of that are studied. By changing the potential of the anode, all that, what is the effect of potential, and the potential, how much potential has been applied. If you apply it in a negative sign, that means the cathode is made positive, anode is made negative, then the electrons are repelled. And then very short, very small negative voltage is enough to stop this currents. And the electrometers were used to measure how much charge is collected. The charge is emitted, and then the charge is collected on some electrometer, and how much charge is collected, that is measured, and that is how a quantitative experiment was done by the Leonard. And then the result of these experiments were these. So the Leonard finally writes. It's very nice uh, to go in detail how the experiment was performed, but these are the results. Electrons are emitted when UV light falls on cathode, so that was one, and they are emitted instantaneously. So that comes from there. Although that time it was not a big issue. When it came, whether the wave theory can explain photoelectric effect or not, then people calculated that no, instantaneous, almost instantaneous emission cannot be done if light falls as waves and interacts as waves. So all those things came later. But at the Leonard time, this was not a very important issue, that it comes out in a very short period, short time after this UV light falls. Okay, but he emphasizes these results. It can be stopped by very small negative voltage, and that tells that the emission emitted photoelectrons have very low kinetic energy, very small kinetic energy, which can be stopped by just a few electron volts of energy. So few volts of this potential. So that he emphasizes in that paper. And then he changes the intensity, and he reports that this speed of electrons do not depend on the intensity. These are very common facts. So you may be wondering that why these common things I'm telling, but I'm telling you the history. And the next slide is very interesting. The next slide is very interesting. So speed of electrons do not depend on the intensity, but if you increase the intensity, number of electrons or the currents, which is the number of electrons emitted per second per unit time, that increases. So these are the results from that Leonard experiments, nothing more than this, right? So it has to be displayed in textbooks in the correct fashion, nothing more than this. It can be stopped by small negative voltage, that's one result. And then the speed of electrons do not depend, that means the stopping potential, that does not depend on the intensity, that result comes from here. And then the current increases if you increase the intensity. So these are the results which and the next slide is when he writes, he explains and discussed his experimental results. He concludes, since the speed of this electron which is emitted when UV light falls on the metal, that does not depend on the intensity of light. That means it is not coming, that energy needed for that escape, energy obtained by this electron to come out of this metal is not from the light itself, is not coming from the light at all, but from the interior of the particular atom. This sentence I have taken directly from his paper, Leonard's paper. Okay, so nowadays we explain it in a very, very different manner, why the energy does not depend on the intensity. We say that number of photons are increased, but the energy of each photon is same, and the whole energy of the photon is. So all those things are our later discussions. But when Leonard did perform this experiment, and he found that okay, I'm increasing the intensity, but the same 2-3 volts of negative potential is able to stop the current. He concludes that all right, the energy obtained by this electron to come out is coming from the particular atom, from that particular atom itself, the interior of the particular atom. So that is how it's concluded. So very nice things to really think of. Go in that era, go in at date 1899 or 1901. What is available? What are the theories which are there? What are the understanding which are there? And in that kind of environment, how the physicists will interpret their data? Those things are really very, very interesting. Now, Millikan again. We all know oil drop experiment of Millikan. Okay, but this experiment of 1930 to study photoelectric effect by Robert Millikan, that is a real wonderful experiment. And the design of his apparatus, that is the most fascinating, and every physics student should go through this particular paper. Okay, this is the kind of picture which is there from his writings. Very complicated. I will not explain this here, but the thing is that he has used some sodium or lithium cathodes, and these three things which are there, cylindrical objects in this right to the middle, which at 120 degrees you can see these three things. I don't have the pointer here. I don't know from where I can bring that pointer, and therefore I'm explaining it. So these are the cathodes. And everything is vacuum, remember. And this is early 20th century, 1913. And his design is such that it can be rotated, and of the three, one can be brought in front of for using in the experiment, and two will just rest. So which one to bring, that can be arranged from outside, you can rotate. And most importantly, if you carefully see, there's a blade kind of thing where all these three cylinders are there at 120 degrees. Left to that, capital K is written, and then you can see a blade kind of thing, and this is actually a blade. So the cathode, particular one of the three cathodes which is to be used in the experiment, that is brought in front of this blade, and then the surface is cleaned every time he takes the data, just before taking the data in the vacuum chamber itself, and in under that vacuum itself, he cleans by that blade, by just scratching the surface from that blade, and every time after fresh cleaning only he does the experiment. And he write in detail in his description that why it is very necessary. If the surface is not clean, even the slightest oxidation will change the property greatly, and therefore every time he collects the data, he does. So it's a kind of workshop in vacuum, inside the vacuum tube. So that design reading will be very, very useful by the students who want to pursue this physics thing. All right. So I term a most meticulously designed experiment. Sodium lithium thing that he used, and inside that he did all that cleaning and blah blah blah, and he used mercury vapor lamp. Now it is very simple to say that you change the intensity, change the frequency of the light source, and see what happens to the intensity and stopping potential, this and that. But changing this frequency of light is not so simple as it is today. Even today, it is not very simple. So Millikan used this mercury vapor lamp, and it has so many wavelengths, 546.1, 433.9. So many wavelengths are there. Discrete lines are there. It's a discrete spectrum. Then proper filters were chosen so that one or other of this wavelength dominates. It is not, you cannot choose, or at least Millikan at those times, it was not that you just choose one line there. But that can also be done by grating or something. You can always isolate a particular thing. But using varieties of filters, he dominated one wavelength in the light source, and then he made the studies. And what were the studies? Stopping potential, basically stopping potential for each wavelength, and confirmed that Einstein equation, h nu minus w, kinetic energy h nu minus w. Now if I go for other literature which were there, and I also quote something from this Millikan paper itself, it is said that Millikan designed this experiment to refute Einstein theory. Because when Einstein proposed this photoelectric theory, it was such a strong deviation from the existing ideas that it was very difficult for the physicists to accept it. Okay. So the experimental results are always supreme, but there can be more than one explanations for, or more than one theories can be formulated which can explain that same data in the same experiment. And people always thought that there's very fishy in that some of the physicists, there's something fishy in this Einstein interpretation. This may not be the right description of the nature. So, okay, good. This theory has is able to explain. Then data. Remember, this frequency dependence was not there when Einstein wrote paper in 1905. Millikan experiment in 1913. And Leonard never measured the dependence of stopping potential on frequency. All right. And so at the time of Einstein, this frequency dependence on photoelectric effect, photoelectrons, was not there. So Einstein formulated the theory which explained that those Leonard results, fine, instantaneous kind of emission, or those things were there. And it does not depend on intensity and number of photons, and the intensity, if you increase the intensity of the light without changing the frequency characteristic, then the photocurrent increases. All those things were explained by the theory. The theory also predicted that the kinetic energy of the electrons should be linearly related with the frequency of the light. So this was a prediction from the theory. And this Millikan is doing the experiment to either verify or refute that prediction. Okay. If he could have refuted, then another Einstein would have been needed to design yet another theory. But, and Millikan also did not believe in that Einstein theory. But as a physicist, he checked it through such nicely designed experiment. Okay, one of the beautiful experiment that or the operators that he designed that time. It was marvel of engineering also. Okay, but then it came. Now I read this or I have quoted this from his Millikan's paper. From his paper. Okay, this is his data. This is Millikan's data. The things that we see in our textbooks, the frequency on horizontal axis, and then this potential on the other, and then the current. You increase the potential, the current increases. You decrease the potential, the current is decreased. And if you apply a negative potential at some place, this goes to 0 and so on. So that is okay. No. Okay, I have not sure. So let me see. Just give me a minute. Just give me a minute. It's not on the screen, but let me try if I can. If I can. I can read from somewhere else. No. Okay. So if you read from the original, in that when he reports this 1913 results and then discusses it, still says that the Einstein's explanation has problems because it's very close to that ether theory of light, and whatever objections were there on the ether, those objections still persist, and this and that. So that also it's very interesting in 2021 when we read this text written by Millikan in 1913 on the paper of 1905, that those things are also very, very interesting. Now there is a question for you. Now there's a question for students. What if the frequency is varied, but the intensity of light is kept constant? Now, maybe if organizers allow, some students can unmute and answer this, or they can write in the chat and organizers can tell me.
Very much, yes. Organizers do.
So if frequency is varied, frequency of the light is varied in this photoelectric apparatus, And but the intensity of light is kept constant. How will photocurrent change when you increase this potential, anode potential?
So students, please write your response. Yeah, already things are coming in. Kevin Matthew says no change in current. One response. Ashwin George says kinetic energy of ejected electron will change. Any other response? So one response says there is no change in current. The other one says
Okay.
kinetic energy changes. The other one says stopping potential increases. Velocity of electron varies, and it goes like that, sir.
Okay. So I'm showing what NCERT says, right? This is the textbook we all study, and it shows the graph. And the text, if I read on the left-hand side, we now study the relation between the frequency of the incident radiation and the stopping potential V0. We suitably adjust this sentence. Focus on this sentence. We suitably adjust the same intensity of light radiation at various frequencies. Same intensity of light radiation at various frequencies, and study the variation of photocurrent with collector plate potential. So on the graph, the right hand side, the horizontal axis is that collector plate potential, and the three curves are for three different frequencies: nu1, nu2, nu3, and nu3 is greater than nu2 and nu2 is greater than nu1. So on the left hand side, where you see this graph, for any of these three separately, if you see one frequency and some intensity, and look at the graph. On the right hand side, you have a current, saturation current, and then it comes down, 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 and at minus capital V, not 1 or not 2 or not 3, it becomes 0. So that's the stopping potential, right? So if you increase the frequency, the stopping potential increases. You have to apply more negative voltage to stop the current. That means the kinetic energy is increased. Fine, very good. So increasing frequency, the kinetic energy of each electron which is emitted, that is, or the distribution of energy, so that average goes out, or the maximum kinetic energy goes up, and therefore more stopping potential is needed. Fine. But if you are above that, if there is some emission, okay, the electrons are able to reach the anode, then when you increase this collector plate potential, the photocurrent increases, more and more electrons reach the anode, but independent of the frequencies, if you apply sufficiently positive plate potential, the current becomes the same because the intensity is same. That is how we are taught. But I have a question on that. I have a question on that. If I have increased the frequency from nu1 to nu3, okay, each photon has gotten now more energy. H times nu1, H times nu2, now H times nu3. All right. And intensity, as we define, intensity of light is energy falling per unit area per unit time. So if the intensity is kept constant, the energy which is falling on that cathode area per unit time, that should remain constant. And if I increase the frequency and increase each photon's energy, the number of photons should go down. Because you have to keep the intensity same, you have to keep the energy falling per unit area per unit time same. And therefore, if the frequency is doubled, if the frequency is doubled from 220 nanometer, you go to 440 nanometer, then each photon energy is doubled. And number of photons which are there will become half. And if the number of photons become half, how can you expect the same saturation current? Saturation current means all the electrons which are emitted are able to reach the anode. If you increase the anode potential further, nothing changes because all the electrons which are emitted from the cathode are already reaching that end. That is why it saturates. Okay. So this is an open question. And with that, I will stop here. And this is people to think, people to work on. If I'm hiding something, come out with that, what I'm hiding. And if I'm not hiding something, then think why NCRT and other textbooks give this kind of plot. All right. So fine, thank you very much. And thank you very much for inviting me in this wonderful session, wonderful event. And my respects to Professor Karunakaran, and that is his the information that we have given about him will inspire me further in my teaching and my interacting with students. Thank you very much.
Fabulous, sir. Thank you so much. Thank you so much for this exciting talk. And one of the first things which hit our face, the audience, is that it is not something which we get to hear on a daily basis. As I made a remark in the beginning, the modern developments in technologies gets hold of the students and they think the modern big data and all the other developments are very exciting, but you picked up something as as simple as a photoelectric effect in the name that we all learned from the high school. It can be, we take it for granted, but then you stuck as with a lightning bolt that if you go to the old papers, the novelty which people came up with, they can inspire us and then bring out the ingenuity in young people. Now, I'm sure that we can spend a few minutes in taking questions, sir.
Yeah,
I
sure.
hope
Sure.
students will be loving to interact with you.
Yes.
So,
yes.
So please start typing your questions, and we'll select few. Please get ahead, people. Start typing your questions. We'll just choose and allow you to speak to sir. Karthik S. Would you like to open your mic, Karthik?
Good morning, sir.
Good morning.
Sir, how
Yes,
about
sir.
photoelectric effect at low temperature, sir?
Temperature. Okay. What do you think? What do you think should be there? Effect of temperature. What does the temperature do?
At low temperature, the superconductivity will happen, sir.
Okay. Okay. That physics is very different, and I do not know. I don't know the superconductivity. Yeah. Okay.
Thank you,
Because
sir.
in superconducting phase, how things will interact with this EM waves, I'm not very sure.
Sir, Ramaswamy sir wants to ask a question. Ramaswamy sir, would you like to?
Sir, can I talk to Karthik little more? Karthik?
Yes, sir.
Yes, sir.
Yeah. So, which year you are in, and what are you doing? What are your interests?
Sir, third UG, sir.
Okay, third year UG. And which topics you are more interested in?
Sir, my interest is quantum mechanics, sir.
Okay. So you want to explore the superconductivity?
Yes, sir.
Does that fascinate you?
Yes, sir.
Okay, wonderful. So you pursue in this line, right? And you come out with the answer to your own question and tell me what it is. Okay?
Okay, sir. I will try, sir.
Okay, fine. Thank you.
Thank you, sir.
So the next question is asked by Ramaswamy sir. May I request Ramaswamy sir to open his mic and ask the question?
Good morning, Dr. Verma.
Good morning, sir.
Balakrishnan, retired professor from Christian College, Tambaram. We have seen each other during the IIT-K conferences.
Yes, I remember.
So it's just a guess that when the intensity is increased, more photons are given out. One photon.
If the frequency is same. If the frequency is same.
Yes, I assume that. And so keeping the frequency same, if the intensity is increased, one photon, one electron emission, that you can extend to more electrons, more color, more photons, more electrons. So the current may increase, is my guess.
That's right. That is true. That is what Leonard has established. And that we understand very well. If the frequency is fixed and you increase the intensity, then more intensity means more energy per unit time per unit area. And for that, more number of photons are needed. And it's not one photon, one emission. Each photon does not really emit an electron, because the electron after receiving, but whatever fraction, say 5%, 1%, 0.1%, 0.0, whatever fraction. So increasing the number of photons will increase the number of electrons, photoelectrons. That is very true, and that is why the photocurrent increases. But what happens if I compare 3 different frequencies? And then I say that my intensity should remain same. Okay, then I have to decrease or increase the number of photons to make that energy same, and that is where the
okay, understood.
And I have never seen an experiment, sir. I have never seen an experiment where any scientist, I mean the published papers which are within my reach, I have never seen an experiment where someone has tried this, keeping the intensity same and then changing the frequency and then studying as a function of anode potential. That literature is not there. Leonard has not done, Millikan has not done, no one has done it, Hirsch has not done also, and no modern scientists have reported this kind of studies. So this is a simulated result that we are using in the textbooks. Okay. And in the simulation, if we make some mistakes, those things will go in. So I'm not still, I'm open to respect these authors, textbook authors. Fortunately, I have not given this diagram in my concepts of physics. Okay. But I respect the authors, and maybe I am missing something. So people can work on it and tell me what it is.
Now thank you very much. This is away from photoelectric effect.
Yeah.
Since I've been associated with you on and off, I think, through your meeting today, I would request the South Indian physics teachers to take more interest in Anveshika programs and spread it to South India. I've been observing that. I couldn't do it in my lifetime because of various constraints. But now that money is there, and teachers are also more free to do things, I'm requesting through you at this meeting to open more Anveshika centers here in South India.
Actually, what I gather from today's event, MCC would be a very nice place, very nice center if we start an Anveshika activity here, and maybe we'll talk further.
Thank you very much, sir.
Nirmal sir also.
God bless you. Okay. See you sometime next convention.
Thank you.
Bye, sir.
It's so nice seeing you.
Thank you, Ramaswamy sir, for the interaction and the insight. I ask Bharadwaj from first BSc to unmute and ask the question to sir.
Nirmal, can I interrupt you, please?
May I know who is speaking?
Balakrishnan.
Yes, sir. Yes, sir.
Yeah, it comes as Ramaswamy Balakrishnan because of the Indian-American confusion of the initials. My name is Balakrishnan.
Oh, sorry.
Is Ramaswamy. We have been putting it as R. Balakrishnan. I'm sorry you called me. No problem. I'm Balakrishnan.
Thank you.
Thank you so much.
Thank you, sir. Now I call upon Bharadwaj from first BSc to ask his question to Verma sir.
So good morning, sir.
Good morning.
So my name is Bharadwaj. I made a simple system with 2 pendulums, sir. But if I keep one pendulum in rest and put another pendulum in motion, it's eventually coming to rest, but it is putting another the pendulum which is initially at rest into motion, and it's happening again until both systems settle.
Right. Where did you make it? Where did you make it?
I have it in my room, sir.
In your room?
Okay. Yeah.
I also have it at my place. I also made it. Okay. So I have 2 small, there's a flower trees some 6 feet high or so, and at a separation of about 10 feet. So I have put a rope between the two trees, and from that rope, I have hanged these two pendulums of equal weight and equal length. Okay, and the separation between the pendulums is variable. I can vary that, and then I do lots of this fun activities with these two pendulums. So what you have done, one activity, you oscillate one of the pendulum to start with. The second pendulum is rest, and then the motion alternates. Okay, one slows down, other picks up, other slows down, one picks up.
Yes, sir. Yes, sir. Yes, sir.
So there is some interaction between the two pendulums through those whatever that rope or string connecting something. You must have connected these two pendulums with something, right? So that
Yes,
is
sir.
providing the interaction. And you are in first year, right? First year BSc.
Yes, sir. So, but if the thing which is connecting both of them is interacting, but I just increase the tension in the rope, I could feel that the pendulum which is in motion is twisting the wire, which is inducing the motion on other pendulum. But if we have only one pendulum in this thing, and this thing doesn't happen also. Like when it swings, it comes to rest. And
that's right. That is right. If you only have one pendulum, is a normal pendulum. Actually, you write to me on email. I will give you some 3-4 beautiful more such experiments with the pendulum. With a single pendulum also you can have very fascinating things. Okay, but these two pendulums is a well-defined theory for that. Two pendulums interacting with each other through some kind of force, and depends, you can tune the kind of force which is there between the two, and different kinds of results are there. So just like one system, one pendulum, one single pendulum, oscillating under gravity alone, it has a particular frequency, natural frequency. It oscillates at that particular frequency. Now, if you have system of two pendulum, and both can move independently, of course that connection is there, but you can forcefully make one pendulum to move, other you can hold, and so on. So there is a freedom, and then you oscillate and leave it. You oscillate and leave it under that interactive force, the weight and other things. That also has natural frequencies. And it so happens you have two different natural frequencies for this system. For a single pendulum, you have just one frequency that time period 2 pi square root L by G. But for two pendulums, it's a more interesting system, because now you have more greater freedom to of the motion. So it has two different natural frequencies, right? And if you have having more than one natural frequency, does it surprise you? If that, then you remember the vibration of springs fixed at two ends. There are so many natural frequencies: fundamental, first overtone, second overtone, and so on. Okay, so now depending on how you start the motion, now it depends what are the initial conditions under which you have started the motion. It will behave in different fashions. Okay, you pull both of them aside and then release. One kind of motion. You start with the two pendulum at 180 degrees and release from there. Another kind of motion. You start with one pendulum fixed, another pendulum, you pull that another pendulum and then release, another kind of motion. You can get hundreds of types of motion with these two natural frequencies, of course, and depending on how you start the motion. So beautiful theory. I'm sure you will perhaps study in the first year itself, the coupled pendulums and the resonance and and normal frequencies and other things that you will perhaps doing in this. But it will be very nice. You write to me, I will tell you more 3-4 experiments. Dr. Balakrishna want to say something?
Thank you, sir. Yes, sir.
Yeah.
Fabulous, fabulous. Now, I would like to ask Kevin Matthew. He has something to ask you, perhaps something to comment on the first question which you left us with. Kevin, can you
Okay.
please unmute?
Hello.
Yeah.
Good
Kevin,
morning, sir.
please. Good morning.
So I was just thinking about the question that you left us with regarding the
Okay.
intensity, keeping the intensity constant.
Okay.
I'm not sure if I got your question completely, but this is what I understood.
Mhm.
That is, if the frequency is increased to increase the energy, then the number of photons must
Mhm.
the number
Go
of
down.
photons must go down, right, sir?
Correct.
At constant intensity.
Correct.
Sir, the way I understand it, like you said that there was no particular experiments that was conducted on this, right?
At least I had not seen.
Okay, sir. So, sir, what I think is, if at all we're conducting an experiment on this and we have to keep the intensity constant, then of course we can't do anything about the number of photons being ejected, but rather I believe that we can adjust the area of impact. That is, as the frequency increases, let the area of impact increase, so that since area will be in the denominator, the intensity will be maintained constant. Even the rate of photons will be constant always. And accordingly we can keep the area of we can increase the area of contact, the area of impact, so that even the increase of frequency will not affect the intensity.
Number of photons, right?
Number of photons per unit area.
Number of photons per unit area. Oh, intensity same means number of the energy falling per unit area should be same.
Yes, sir. Yes, sir. So that's like NH nu by AT, right, sir?
No. See, you have a light source, right? You have a light source. You are not changing the position of the light source, and then at some distance you have your this plate. Okay. So now on the plate, you are already receiving a stream of photons, which you are not changing. Okay. If you are increasing the area of the plate, yes, more photons will fall on that increased area, but per unit area.
Sir, I mean, not the area of the plate, but rather the area of the source of light, sir.
Okay. You are changing the source itself. You are changing the source itself. You are changing the geometries. See, if I have a mandate, okay, if government of India tells me that you design an experiment where we keep the intensity constant, we change the frequency, and photocurrent should not change. All right. So I can always design that experiment, and I can take your idea to change the shape of the source, increase the area of the source, and so on and so forth, change the geometry so that the intensity remains the same, frequency is different, still photocurrent, and that NCRT picture is justified. Fine. So if I have to do that, I can do that. But that is not what is meant by that NCRT text. It says that in the same photocell, in the same experimental setup, if I just change the intensity of that light source, not by changing the light source itself, but by changing the knob which controls the intensity, right? Just as regulator controls your fan speed.
Yes, sir.
So that is how that is meant. What you are saying is okay. We can always design different kinds of sources with different surface areas, different geometries, so that the final intensity of the source is same, but still that per unit area falling on a particular surface in a particular geometry. So those things can be done. Yeah.
Sir, so like what I was saying, what I was thinking is that the knob which adjusts the intensity of the source of light will also be connected to a particular shutter, like a shutter which is which is in front of the source of light, like the slit width, like how we adjust the slit width and all in the spectrometer and all. or in the camera we have a shutter so that we can take a
yeah. If the net goal is, if it is so important to have that net goal, that we have to keep the intensity same and we have to keep the saturation current same, then we can think of different kinds of designs. But is that important?
In order to keep the intensity constant, I think that is a part of keeping it constant, sir.
Okay.
That's all I thought. So just one more thing.
Yeah. Good that you can think of new designs to achieve a particular kind of result. That's a good attribute. If you have something that, okay, I need this thing to happen, and then what kind of apparatus I should design. So you have that that capacity to think of. So that's good. That will help you in your further career.
Thank you, sir.
Physics career.
There's just one more thing I wanted to ask. It's not related to the photoelectric.
Can we just move on to another participant? Just we have a limited time. We cannot.
Okay, sir. No problem.
Thank you for the question. I would like to request Kani Mori to unmute and ask. She has a general question to ask, but maybe keep it brief, please.
Okay.
Ms. Kani Mori.
Good morning, sir. Thank you, sir, for providing me this opportunity. Sir, I have a question for you. Why does time seem to flow in one direction, sir?
Oh, that's a very difficult question for me.
I saw many answers in Google for this, sir. I want your answers.
No, I don't want to get into it because if I get into it, then I have to go much deeper and understand the things. My life is simple with one direction of flow of time. I do not want to change it.
Right.
Kani, which year you are in?
I am first year and I am from RMD Engineering College, Computer Science Engineering Department, sir.
Okay. Very good. So you like computer science?
My aim is in taking space science, sir.
Space
through
science,
engineering.
okay.
Yes, sir. Through engineering, I want to achieve my dreams, sir.
Very good. So during the summers, do you plan to go, or you have gone to these space centers, Ayuka or ISRO, or have you contacted some people there?
I am attending some online courses, sir. Through that only I am able to.
Okay. It's nice if you can interact more closely. You can spend, because all these institutes do have programs for students. All right, 1 week program or 10 days program or summer internship like that. So you can explore those things and then contact them and use your summers and other things for these things. Once you see once you interact with the people who are into it, that can shape the things very nicely. Okay, thank you, Ken.
Thank you, sir.
Sir, we have 2 more questions coming in. Can we take them with your permission?
Please go ahead.
So I request Dr. V. Ramesh Kumar Vaduganathan to ask his question. Please unmute, sir. Okay, go ahead.
Good morning, sir.
Good morning.
Sir, this is my any general questions. Because you were telling about the photoelectric effect and so on. So the photon having some energy, sir. Photons also have energy.
Right.
So once, is it possible the photon can will hit on the object? Is it possible to move that object, sir?
Yeah. If you see possible, not possible, yes, it is very much possible. Then comes the engineering aspects that to make that motion visible, measurable, your operator should be sensitive and all those things. So all those things are there. These photons do make all our atoms to vibrate with their frequencies.
Okay.
All kinds of optical phenomena, just a minute. All kinds of optical phenomena, whether it is reflection, refraction, this, that, many of these things, scattering, these things come about because the photons which they hit the surface, they make part of. Right.
So in this way, why don't we think the photons, the light energy is enough to rotate or move or spin an object in a space? Is it, sir? Is it possible?
That's what I said, that now it's the engineering aspect. Now it's the engineering aspect. You have to design the system so that the photon energy, you know how much photon energy you have available with you. And then in what directions and all those things, how much momentum it can transfer in how much time and so on. So with that, a macroscopic object, if it can be moved, how much it can be moved, and then all the other factors which are there, the frictional torque and this and that. So those engineering aspects are there. And this 1913 paper, if you read of Robert Millikan, which I mentioned, you will see that how he has addressed all these issues, and he's designed things. He's designed things. So those kind of engineering aspects are there. But yes, in principle, yes, why not?
Why I am asking this question, sir? Actually, generally we know that our planets, the planets spin around the sun due to the gravitational force and so on and so we know that. But why don't we think the sun light energy push the planet to spin? Why don't we think like that in this way? So that's why I have this questions in my mind. I asked in the research gate also, but I get a negative answers from other side. But now I have the opportunity to ask you this question.
You got a positive answer at least. Or non-negative, at least non-negative.
Okay, sir. Thank you.
Right.
Thank you, sir. Sir, one more question is there. We'll take it from the second BSc Physics student, Mr. Vikas. Vikas has a kind of a special question. Vikas, can you please unmute and ask the question yourself?
Yes, sir. So actually, I recently heard about this experiment called the muon G2 experiment. So I don't really know what this experiment is all about. So can you explain a little bit about the experiment and also the results? So what are the results about?
You're asking a very specific thing. Can you have to tell us a little more?
The thing is, I really don't know about the experiment.
Oh, then you are kind of.
I just wanted to know about it.
No, that is not very helpful. So.
Right. You first read wherever you have seen that experiment, write up or wherever. You read that. You try to understand how much you can. Okay, and then you can contact me. And if I am able to explain more, I will do it. Otherwise, I will connect you to someone who is in this field, and you can interact with the person. Okay.
Sure, sir. Thank you.
But you have to do first your homework.
Yes, sir.
Okay.
So inspired by your talk, many students will resonate with Kevin Matthew, who has the second question. I'm just going to read it for the brevity. He is interested in mathematical physics and has an inclination towards grand unification and string theory. He wants to be a teacher like Feynman. So he wants to know what your recommendation would be to the students.
Go ahead. And if you want me to tell you people who are working in these fields, grand unification, string theory, this, that, I can connect you to some of them. And then you can hit on the right kind of literature and right kind of strategies, and to become a good teacher. Yes, that's wonderful. Okay, and there's a good occasion to have that kind of oath that you become a good teacher. Thank you.
Another one last question that is from me, because these are challenging times. I understand, everyone understands the relevance of a teacher has somehow, it seems to have been diluted because of this technologies that has come around. And this is the antithesis of the current feeling. Today we are having you represent the very antithesis of the common perception of the younger generation. We don't need teachers, resources are there. So I want you to say a couple of words to our own teachers to strengthen our resolve to teach students better. What would be your message to our teachers, fellow teachers?
In fact, every challenge comes with an opportunity, right? Because of this internet availability, because of so much of resource material which is there on the internet, this question arises. When these things were not there, classrooms were the place where the science was discussed, and the teacher had a great role. But now that we have all kinds of online courses from whatever university, good university you want is there, and you have any question, there are so many websites where people are there to answer your question and other things. So a classroom teacher, the relevance seems to have gone down. But in the earlier days, I had access to only my classroom, my students, 50 of them. That's it. That's it. But now I also have access to 50,000 of them. Okay. So every challenge comes with an opportunity. That time when I was teaching photoelectric effect at Patna Science College, 1980s, early 80s, that time I did not have these resources where I could tell them an interesting story about it. I could not tell him about, I did not know about that Millikan's experiment. I did not know that Millikan has also worked in photoelectric effect. I only knew that he has worked for that determination of electronic charge. So for me also the opportunity is there. And then now I have to think this, that textbook stuff is available on the net. Yeah, you have to solve a particular differential equation, it is very much there, right? You have to solve Maxwell's equation, it is very much there. You have to do this hydrogen atom Schrodinger equation, eigenvalue, it's already there. Fine, good. But what is not there? What is not there? What is there, but it has not been designed, decorated, and written in a fashion which can fascinate people. We can hit on those things, and the teacher will never lose the relevance. A good teacher, a teacher who is ready to exert, a teacher who has this newer ways to present things. See, teacher means if you have the same syllabus, 5 years, 6 years, 10 years, you yourself will be annoyed with that. The same story every year, the same story every year, the same story every year. How many times? And that is how that the thrill, the excitement goes down. The teacher's problem. So if a teacher is always innovative, not in designing new experiments only, whatever presentation, examples, jokes, every year you crack new jokes in the classroom. So that is also an innovation. Every year you have to think of something new. So if that is there, those cells are active. Okay, so whatever is the condition, you will find opportunity from that only.
Perfect, sir. Thank you so much for a very well thought out response to our question. I believe the teacher community will take it to their heart and then move on with the innovative ideas. Now, as a formal vote of thanks, I request Mr. Blesson, who is the General Secretary for the Society, Physics Society, to render his vote of thanks, a formal vote of thanks. Blesson, please.
Good morning, everyone. It's my honor as a chairperson to give the vote of thanks for one last time. First of all, I thank the Almighty God for showering us His immense blessing to conduct this lecture and making it a successful one. I would also like to thank the star of the day, Padma Shri Professor H.C.Verma, the one name which every physicist of our generation would have heard from our childhood. We are very grateful, sir, for accepting our invitation and enlightening us with your immense knowledge. Thank you, sir. I would also like to thank the principal, Dr. P. Wilson, for honoring our chief guest. And I extend my thanks to Dr. N. Lakshminarayan, the president of Physics Alumni Society, for the presidential address. I also thank our head of the department, Dr. P. Samuel Ashirvadan, for the welcome address. My sincere thanks to Mr. Amit Kumar Bajpayee for helping us connect to Professor H.C.Verma and making this dream lecture come true. I would also like to thank Dr. Sam Pauldy, Secretary for Physics Alumni Society, who worked tirelessly for coordinating all our alumni and making such events possible. We are especially thankful to Dr. E. Caroline Victoria, our staff advisor, without whom this lecture would have still remained a dream. I would also like to thank Dr. Nirmal Tyagu, who has been a wonderful host. I also extend my thanks to Dr. James Kurian, Vienna Committee, for approving the lecture. I also thank Dr. Ashik Bonafar for helping us access the online platform Zoom for conducting this event. I thank Mr. Nitin of 3rd BSc for the invite, Ms. Nikita of 1st BSc for the PowerPoint presentation, and the 2nd BSc students for the prayer hymn. Finally, I thank all the retired professors, students, and all others who have accepted the invitation from our department and making our event complete by a kind presence. Last but not the least, I would also like to thank my cabinet, my teachers, and all the students of the Department of Physics for making this event a grand success. Once again, thank you all.
Thank you all. Thank you. Thank you, sir.
Thank you. Thanks a lot. Thank you, Nirmal. Thank you.
Thank you, ma'am. Thank you. Thank you.
Thank you, sirs.
Thank you.
Thank you. Thank you. Thanks a lot.
Thank you, sirs. This is from him, Samuel Asirvadam. Thank you, RBK sir. Thank you, all of this.
Aram sir.
Thank you, sir. Aram sir, everyone, sir, everyone. Thank you very much.
And people who from other colleges and other institutions. Thanks a lot for accepting our invitation. I hope it was useful to you. Thank you. Thanks a lot. Shall we close the